Okay, so let's continue. Last week, if you remember, we tried to calculate the speed of the expansion of the universe, right? And then we got this value, right? 3 times faster than the speed of the light. Is this okay? Isn't this against the general relativity, where Einstein said the fastest thing in the universe is the speed of the light? Does anyone know the answer to this? Have anyone thought about this? No? How about Ashwin? No? Okay. This is okay because Einstein said that actually if you're careful about general relativity, the fastest the speed that information can travel through is the speed of the light. So that's what general relativity said. But this is the expansion speed of the universe. And it's not, information is not traveling at 3 times faster than the speed of the light. So that's why, in short answer, this is not, inconsistent with general relativity. For example, say, okay, maybe Anson and myself are 2 galaxies in the universe, right? And then we're on a carpet. Say there's a red carpet between us. That's universe. And then we're moving our way. But then if I move from Anson at 3 times faster than the speed of the light by running, I'm good at running. Maybe I can run 3 times faster than the speed of the light, right? Then if I run 3 times speed of the light, then that's against general relativity because I'm traveling faster than the speed of the light. But situation here, expansion of the universe, is not like that. Both Anson and myself are stopping on a carpet. And then this carpet is moving away, if you squeeze carpet and then push away, the things on top of the carpet also moves, right? Carpet is moving at the speed of the light, 3 times speed of the light. So I'm sitting, he's sitting, and then just carpet is expanding. That's the situation. And then here, no information is carried between us because I'm just sitting. If I'm running by myself, I can go there and then tell, okay, Anson forward the format. I can tell the information, right? But I'm on a carpet, so I'm not moving. So I cannot tell that anyone that Anson forward the homework information, right? So there's no information is going with the speed of the light. So that's why this is not inconsistent with the general relativity. Okay. So this is about here expansion is expanding. What's expanding? It's space-time, not an object is moving. So that's the difference from general relativity. Okay, then that's the answer to the last question in last week. And then now, okay, I can show you an interesting movie that I created. Is that my here. Maybe this one. Yes. Here. Who is this good-looking guy? Anyway, so I can explain here. Okay, let me explain. So this is a situation, here I have a rubber band, right? And this is going to, I'll just explain what I'm saying in the video. When universe is not explaining, the light comes from one side to the other side, right? I'm going to show in a minute. Okay, here in the universe, when universe is not expanding, okay, maybe I should ask you a question first. Okay, so Alex, do you know the age of the universe now?
Age 13.8 billion. 13.8 billion.
Yes. 13.8 billion years, right? So okay, that's what we know from the various observation. However, the size of the universe now is 400 billion light years. Right? How can that happen? Okay, the universe is only 13 billion years, but the size of 40 billion years. Size of the universe is like 45 billion light years. How can that happen? Isn't it weird? Okay, question.
Maybe because our universe initially has some space, so it can be spent more than the year.
That's a good point. Maybe that's the case. But if that's the case, the universe may be bigger than 45 gigalight years, billion light years. But in this case, let's assume the universe starts from one point, Big Bang, and expand in 13.8 billion years. But the size of the universe now is 45 billion years. Can anyone explain? So that's what I'm trying to explain here. Okay. If universe is not expanding, then this is 13.8 billion years, right? Light years, right? Because that's the size of the universe, right? And then light can travel from here to here in 13 billion years. But the universe is expanding when the light is emitted from the right side, and while light is traveling through the universe can expand, right? Right, like this. Okay. And then the size now is actually 47 billion light years. Does it make sense? Do you understand it?
Mm-hmm.
So the light was emitted from here, and then it took 13 billion years to reach me or the Earth. But then during that time, light is traveling, universe is getting bigger. So now the size of the universe is 47 billion light years. Does it make sense? Okay. A lot of people, including professional astronomers, confusing this. So when we say the universe is 13.8 billion years old, it doesn't mean universe is 13.8 billion light years size, right? Well, it's so easy to confuse, right? So when we say the galaxy that Alex found, how many years ago? Do you remember? Redshift 4. 1.4 billion years ago, right? But that doesn't mean 1.4 billion light years away, right? In terms of light year, it's much bigger number. But then people confuse and say, 1.4 billion light years away. It's interesting. Professional astronomers confuse that because it's easy to confuse. But you guys are not confused now, right? I hope.
So when we talk about the distance of the source, do we mean that we are in the moving free mode, right? We don't include the expansion of the
Sorry. This is including expansion of the universe, because this number is changing with the expansion of the universe. So this is proper physical distance. That was a good question. Okay, then we can go into more about distances. So, okay, Anson reminded us good things. So we talk about co-moving distance and a proper distance, right? And then, in a little bit more detail, in the universe there are three definitions of the distances. And then in a flat Euclidean non-expanding universe, those three are the same distance. They just return the same number. But because universe is expanding, those three will give you the different numbers in distance. So please be careful. That's one of the topics today. So these three, angular diameter distance, and then proper motion distance. Proper motion distance is co-moving distance in a flat universe. So this is sort of like co-moving distance. And then luminosity distance. Okay, let's look at it one by one. Angular diameter distance, the definition is very simple. So the definition of angular diameter distance is this. So this size d divided by theta angle. So that's the angular diameter distance. So as you can imagine, if this distance is larger, this, what happens? The angle becomes smaller, right? If this distance is larger, this angle gets smaller, right, for the same size. So this gets smaller, so this gets larger, right? So we can measure the distance in that way, right? Okay. For example, D is the, say it's a ruler. This is 1 meter, okay? And then we put 1 meter here and then there and then more distance and then measure the angle. And then by that we measure the distance. If it's 1 meter, this ruler is more distant, it's smaller. And then if it's nearby, it's larger, right? So we can measure distance that way. We can do that in that, we can measure that in a distance like this, right? Okay. Now, actually our eyes are doing this. Our eyes has two, right? And we measure the angle, right? And then we see it's far away or nearby, right? That's why we have two eyes, right? So that's sort of our eyes are doing. Okay. Then that's fine, right? And then next one, proper motion distance. And now we define this thing. It's very similar, but in terms of velocity. Okay, so definition is here. So u is a velocity here. Velocity of some object moving this way. This is physical velocity, kilometer per second, something like that. And then divide by the angular velocity, so the change of the angle. Okay, it's similar to this, but in terms of velocity. So suppose something is moving, okay, and then say this object moving 1 meter per second, and then how much angle is going to change as a function of time. So that's the definition here, right? As you can imagine, you might think these two are same. No? It's actually same in a non-expanding Euclidean universe. Because if you put 1 second or some fixed time here, this becomes this, right? If you say 1 second, then it's fixed distance. If you say 1 second, fixed angle, so it becomes this. So it's the same, right? Okay. But now, okay, then the third one, okay, is luminosity distance, okay? Luminosity distance, maybe this is also very intuitive. Luminosity distance definition is luminosity divided by 4 pi s. S is a flux, and then square root. This makes sense because the light, say there's a light bubble, and then to put it more distant, it becomes fainter, right? If you have, say, let's say candle, and then you put it nearby, it's bright. If you put it far away, it's faint, right? And then measure distance that way. And how much does it become fainter? We actually know that, right? It's proportional to inverse square of the distance, right? So that's why. So this is distance. So if you take square, then square, and it becomes inverse. So inverse square. Okay, maybe I should say. So the flux, apparent brightness, is intrinsic brightness divided by 4 pi distance square. We know that, right? So we modify this into this, and then make it as a this as a definition of the distance. Okay. And then, well, this probably, you know that, probably you're familiar with this. So these three in our high school universe is the same thing. But it's not the same in our universe. They're all different in our expanding universe because the universe is expanding. Okay, let's look at that. Okay, now, okay, now we go back to the Friedman-Robertson-Walker metric. Okay, then it's the same thing, but then this is size is d, angle is theta, and then this distance we use r and r1. What is this r? It's a scale factor of the universe, right? And then this large r is going to change when universe expands. You know, when universe becomes twice larger, this r is twice larger, right? So we include r, expansion of the universe, in this r scale factor. Okay. Then let's think about Friedman-Robertson-Walker metric. Angular diameter distance. Definition was d, this divided by theta, and then this d, actually you can use this to express, right? You can use r theta r, right? This, when theta is very small, tangent theta is theta, right? So you can multiply this, and that's d. Here, that's d. And then, okay, you can cancel the theta, and then it becomes r, large r, and then small r. Okay? So that's the angular diameter distance. Okay? Then we can do a little bit more. If you remember the definition of redshift, it's this, right? R1 and R2, how much the universe expanded between R0 and R1. It's 1 plus z, right? You remember? 1 plus z. So we can replace this as 1 plus z and R0R. We can write it down that way. Okay? Then, okay. Now, this is angular diameter distance. Now, how about proper motion distance? Okay, we can velocity. Velocity we can also write down. This was definition, right? D divided t, and d is r1 r theta, so this divided dt. Okay, and let's put it in a definition of proper motion distance. Then definition is this: velocity divided by angular velocity. That's the definition. And then velocity we can write it like this: r1 r theta, and this dt. Okay, you have to be careful now. This t dash and this t is not the same, because this, we go back again, maybe here. So this t is our time frame, right? We observe it, and angle is changing, that's our time, right? This velocity is at that time, right? They're at some distance, right? So we learned last week these two times are different, right? It's this time dilution. So how much is the time dilution? It's here. The difference of time dilution, actually, this is also a definition of 1 plus z, right? So when we do this, we have to be careful. So this part, dt dash dt is actually r0 divided by r1. So we put this in, and then what becomes like this. It's dr and r0, r1 and r1, and then it becomes r0. Okay. Then let's compare with the previous one. So this one, r1r, is the angular diameter distance, right? And if we use the velocity, proper motion distance, then we got r0, right? This is r0, this is r1. So it's not the same thing, right? If the universe is not expanding, then r0 equals r1. So that's same. But when the universe is expanding, those two gives you different number. Okay, so that you need to be careful. Now, the last one, let's look at the luminosity distance. So using a candle. Okay, then now we think about this kind of situation. So the universe is expanding this way, so that some object is at this distance, and then universe expands to R0R. So this is R1R, R0R. Then let's look at the luminosity distance. Then to calculate the luminosity distance, we need to calculate the area, right? Area of the flux propagating. And that's 4 pi r squared. And what is r now? R is this, right? R squared, okay? And the energy it emits is LTT in a short time scale. But again, you have to T dash. This is time frame of the source. And then there's an energy loss because of redshift, because the wavelength gets longer, right? So that's this factor R1 divided R0. Okay? And then flux received is here, S. Flux is energy, but there's energy loss as a function of time. And then it should be divided by the area. So that's the flux S we're going to receive. Okay? And then we work on this, and then go, and then what we get is we get here and get here. Okay. And then so with this we get this. Luminosity distance is R square R divided R1. And then, this R0 divided by R1 is 1 plus Z. So actually you can write it 1 plus Z times R0R. Okay. Okay. Now what's the relation between those three distances? Okay. Giselle, what's the relation between these three distances? Hmm? I don't know. What are the three distances? Do you remember?
Three distances?
Oh.
Lights to our eyes.
Hey.
Lights to our eyes. Is it one of them?
Okay, I can remind you. Okay, maybe you can pay attention. So the one is angular diameter distance, right? Which is R1R. So the another one is proper motion distance, R0. Okay, not R1. This is R0. And then the last one, luminosity distance, gives you here 1 plus the R0R. What's the relation of these three? Okay, so Arian. What's the relation between these three? There's a big hint here. How many factors are they different? DL and DM and DA.
1 plus Z times.
Yes, exactly. So luminosity distance is 1 plus Z times proper motion distance, and the proper motion distance is 1 plus Z times angular diameter distance. So proper motion luminosity distance is actually 1 plus Z squared times angular diameter distance. So that's the relation between distances. As you can see, if you remove the Z, if you remove the expansion of the universe, these are equal, right? But because the universe is expanding and then in the past, Z is not 0. So that's why these three gives you difference. And then, as you can see, there's no cosmological parameters in here. So it doesn't depend on cosmological. In what kind of universe? in any kind of Einstein considered universe or dark energy dominated universe, this holds true, independent of the cosmic parameters. Okay, so you have to be careful. So I said that in a flat universe, this dm is a co-moving distance, right? And then this angular diameter distance is like physical distance, right? Like kilometer, or meter, centimeter. These are angular diameter distance. And then difference is 1 plus z. So difference become at the redshift is very small number. Those are similar, right? The difference is very small. But when you go to high redshift, what is the redshift of the CMB, Ashwin? You know? What is the redshift of CMB? 1,000, 1,000. So what's the difference between this and this? At redshift 1,000? It's 1,000, right?
Yeah.
So at redshift 1,000, this is one. These two differences, the same thing. Two objects are like here, and then difference in the number is 1,000. Not even going to the redshift 1,000, but if you go to redshift 9, the difference is 10 times different, right? So you have to be careful, especially when you talk about high redshift universe, which distance you're talking about. Okay, say, oh, I observed the area of 10 megaparsec at redshift 9. Does that mean 10 megaparsec in co-moving distance or 10 megaparsec in angular diameter distance? There's a 10 times difference. So you have to be careful which distance you'll be talking about.
So
Question? Yeah.
How we decide to choose which distance we want?
Oh, that's so depending on the physics. Okay, so if you are talking about cosmology, you want to cosmology or a very large scale thing, then you want to exclude the expansion of the universe, right? So then co-moving distance is convenient. But then, say for example, you are talking about gravitational effect, say gravitational lensing. Oh, what's the impact parameter of this galaxy, lensed galaxy? Then gravity works on physical units, right? So you should talk about this physical distance. Because co-moving distance change, it's not, when you calculate gravity, you need to use physical distance, like unit in kilometer or something.
How about luminosity distance?
Oh, so luminosity distance. So, for example, if you want to measure the distance based on type 1 supernova, then you should be using luminosity distance. Or you want to calculate distance modulus, like m minus m, then you should be talking about luminosity distance. The luminosity distance is obvious, isn't it? If you're using luminosity, you should be using luminosity distance.
Oh.
So, okay. So, yes, question?
Is it true for unexpanding universe also? The relation or the distance?
It's true, but if you're not expanding, these three are the same. And if the universe is not expanding, there's no redshift. This R0 and then R1 is equal. So this is 1, right? So this is 0, right? So it's actually, this becomes all, the same. So in our daily life, these three gives you the same number. Because we don't usually consider expansion on the Earth or in a classroom. Okay. Then, okay, we are not going to do that, but we just did the distance, right? And then we talk about 3 different distances, right? And then you can easily imagine there are 3 different volumes, right? Because distance is 3, so when you calculate the volume, size of the universe, or the volume of the universe, then there are 3 numbers, right, based on this. With calculation, it's a little complicated, so we don't talk about the volume, but then, please note, when you, even when you're talking about volume, you should pay attention which volume you're talking about. And then here's an interesting thing that I want to show. Okay. And then in this expanding universe, very interesting thing happened. So this is plotting angular size of something. Let's say a galaxy. Okay. Then as a function of redshift, angular size. So it's how many degrees. When you look at 1 degree or half a degree, 10.1 degree, something like that. Then as a function of redshift, right? And usually, say, look at angular size of, say, this. And if I put it far away, the angle becomes smaller, right? Right. That's our common sense, right? And then actually, we should look at this curve. And actually, at the beginning, when you put an object, farther universe, it becomes smaller and then smaller and smaller, right? That makes sense, right? You put it far away. But look at here. Okay? It becomes larger. Why? So this is actually true. This is happening in our universe. If you put it farther away, say around redshift 1 or farther, it becomes bigger. So you put it right. If you put it, gets smaller, and then it goes beyond redshift 1, it becomes larger. Because our universe is expanding. Okay. The very short answer is the same as that in my video. I forgot. So when you go far away, then at redshift 1 and 2, 3, when the light was emitted, it was closer. Okay. Okay. So you're at redshift 1, okay? And then you emit this galaxy to me, right? Right. And then, it takes a long time to get me, right? And then when I put this far away, so actually when he emitted the light to me, he was closer to me. So when he was here, it was big. But it just took a long time to get to me because the universe is expanding. And now he is far away. But this thing, when he emitted to me, was close. That's why it's bigger. Does it make sense? That's a very simple explanation. Did you get that? When he emitted the light to me, he was close. That's why size was big. It just took a long time to reach it to me. And of course, now he emits the light because he's distant. It's going to be small, right? But he emitted this light when I was very close. So that's why it was bigger. So this size is now kind of far away. But when it emitted the light, it was somewhere around here. Does it make sense?
Yeah.
So that's why this happened. Oh, I should have explained. This curve is calculated from the definition that we calculated above. Okay.
Why is the vertical axis has unit?
This is a milli-arc second, sorry. It's too small, but this angle, so it's very small milli-arc second. Well, it doesn't matter, unit doesn't matter because this is just relative thing. So, well, this is kind of convenient for us, right? Because our telescope have a limited size of resolution, which is usually determined by lambda divided by the diameter of the telescope. So its angular resolution is limited. But then, if when we study the very distant universe, if the size becomes smaller, 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 it's difficult to study those galaxies, right? They become smaller, smaller, smaller. But then it doesn't get smaller, so it's easier to study the shape of distant galaxies. Again, these distant galaxies are closer when they emitted light, so that's why we can see the size. But that doesn't mean they don't become fainter. They become fainter. It's just the size. It's bigger, but then its flux becomes fainter. 1 plus d to the power 4. So it still gets fainter, but in terms of size, it helps. Okay. All right. Okay. Then, next is very interesting topic. Then, what's the fate of our universe in the future? I hope I can finish this today. Okay. So this is quiz. How much does the galaxy become fainter when we put it? Okay, we learned the science scales like this, right? What about the surface brightness? Surface brightness is defined here. The flux per unit angular area. So angular area, and then if I put galaxy farther away, how much does it get faint? We can actually do this calculate this with what we already learned. The hint is angular diameter distance scales like this, and then luminosity distance scales like this. So the ratio decides how much it gets fainter. And actually, the answer is 1 plus d. I hope you can find it. The answer is 1 plus d to the power minus 4, not 3. You might think, okay, the universe is 3 dimensions, so it's 3, but it's 4 because the light loses energy as well. So 3 dimensions plus light loses energy, so minus 4. So 1 plus d minus 4, so it gets very fainter. At redshift 1, 2 to the power 4, so 8 times fainter galaxies are. So it becomes very, very quickly fainter. So that's why we need big telescopes. This is very important, so if you have time, please try to work it out. Okay. Alright. Okay, then another thing about another important words that we often use in astronomy and cosmology, which is called K correction. Because of the redshift of the universe, the wavelength changes, right? That we discussed a little bit last week. So say this, I don't know, this say wavelength at 2500 angstrom, then at redshift 1 it becomes 5000 angstrom. This shape of the wavelength of the emitted light shift as 1 plus z, right? So, but our telescope can usually observe the fixed at the wavelength. Say, we have a filter to observe 5000 angstrom light, okay? Then, if the galaxy is nearby, it observes galaxy's light emitted at 5000 angstrom, but if the galaxy is at redshift 1, the wavelength is twice longer, so we actually observe the light emitted at 2500 angstrom as in the 5000 angstrom filter in a telescope. So the observed light in a telescope filter changes as the galaxies go too far away at higher redshift. So we need to correct all that. Say, even if we observe at 5000 angstrom of the telescope, but its galaxy's light is at redshift 1, it's emitted 2500 angstrom, and the actual 5000 angstrom light from the galaxy is actually 10,000 angstrom. So we need a correction from here for the wavelengths, and then that's called K correction. Okay. just please remember the term called K correction. That's just the wavelength difference that's corrected. How do we correct for this? There are different techniques, but we usually need to assume that the galaxy's SED shape and then calculate estimate the correction. There are many detailed ways papers talk about this. But anyway, I want you to remember when people talk about K correction, they are talking about this correcting wavelength difference. Okay, now we can go to the fate of the universe, which is, I think, very interesting part. Okay. Do I need to do this volume thing? Okay, so now we talk about, okay, we don't do the actual calculation, but I can explain what calculation is trying to do. Okay, now we came a long way, right? Let's go back. Our history of 2 weeks of learning. We started from Einstein equation, put the Friedmann-Watson-Walker metric to describe the expanding universe, right? We talk about scale factor, redshift, and then we define the distances, right, today. And then we can calculate the volume, right? Volume of the universe, because we know that we have way to calculate the distance, so we can calculate the volume. So that's what we're going to do. So we are not going to do it, but I show you what I'm doing here. So you can calculate, to calculate the volume, you can calculate a small piece of, square, right? And then integrate the whole universe. Say small volume, you can calculate thickness and area, and then volume, small volume, each volume can be calculated something like this. And then now, you need to make it co-moving volume. See, we have two different volumes, proper volume and the co-moving volume. We discussed these are different, right? But now we want to co-moving volume. So co-moving volume is going to be something like this, and you can see it's 1 plus z, 3 because this is volume. And then now, if we know the volume of this small thing as a function of redshift, we just integrate this volume from redshift 0 to infinite. Then we know the volume of the universe, right? So let's do the integration. So the integration is here. I did it for you. Say this is small volume, dv commoning, and then I did the integration for you. What a nice teacher, right? I'm not asking you to do it. Well, I didn't do it because it's so complicated. I just copied from the answer my textbook. Okay, textbook did it. Okay. So, well, actually, it's difficult. You need computer to do this, right? You cannot do it by hand. Okay. If you do calculate the volume of the universe, assuming cosmological parameters, and then you get this, the answer. And then, as you can see, the answer, so this, you integrate this as a function of redshift, z, and then as you can see, this depends on the cosmological parameter, right? Here, omega matter, Hubble parameter, these depend on the cosmological parameter. And then now, this answer also depends on the cosmological parameter. So here, omega matter, so amount of dark matter in the universe, and this is omega lambda, amount of dark energy in the universe. So depending on this parameter, the answer is going to be different. And then this shows you a very interesting thing. Here it's in a different color. The answer is in a different color. But say, what should you say? Okay, say if there's no dark energy, if there's no dark energy, there's only dark matter, then it's going to be Einstein Tochida universe, and then it's going to collapse eventually, some big crunch. Because if there's no dark energy, the dark matter or matter is just gravity, right? Gravity is a pulling force. So eventually, even if the universe is expanding now, eventually the gravity stops expansion and it collapses. So that's this area. If dark energy is less zero or less negative, the universe is going to collapse into zero volume, right? And then if there's a little bit of dark energy in this blue area here, and then it can take over the pulling force of gravity, then universe can expand forever. But in this area, dark energy is not enough. So in this area, there's a little bit of dark energy, the universe is not going to collapse because there's a dark energy, but the gravity is going to break the expansion, so the expansion speed gets slower. But still, expand forever in this area. What's interesting is this green area. If dark energy is a lot, and then it's more than the gravitational pull of dark matter, then universe is gonna expand forever, but the expansion speed is going to accelerate even from now. So the expansion speed gets faster. That's this green area. Okay, so the green area accelerating expansion. Blue area speed is getting slower but still keeps expanding. And this gray area, it goes to big crunch. It's crowded. So that's we can calculate from that our equations. Then you may know that our current observation, I think I showed last week, it's around 0.7 and 0.3, right? So current value is somewhere around here. So our future is this accelerating expansion. Is that, as far as we know, that's our future of the universe. And that's interesting. Okay. This fate, okay, here's one example of calculating. See, omega lambda equals 1, then what happens is you put 1 here, and then you get this kind of universe. So this R, scale factor or size of the universe, is proportional to exponential so exponential expansion of the universe. So if there's a dark energy, then exponential expansion, the size is exponentially become bigger, right? With t. So that's one solution in this case. Okay. Then now interesting thing is well, now interesting idea is that okay, next we can talk a little bit about cosmological event horizon. So if the universe keeps expanding, and especially we also learned at the edge of the universe, expansion speed is 3 times faster than the speed of the light, right? Then can the light from galaxy say, okay, we learned earlier today that the edge of the universe is expanding, moving away from us at the 3 times faster than the speed of the light. So if this galaxy emits the light now, can we see it now? We cannot, right? Because, okay, say Anson is at the edge of the universe and he emits the light, but the carpet is expanding 3 times faster than the speed of the light, so I'm moving away from Anson 3 times faster than the speed of the light. So Anson's light, it will never reach us. Okay. So if Anson asks me a very difficult question, I should move away faster than the speed of the light, then I never hear your question, right? Okay. So that's what I should. Anyway, then we can ask a question: how far can a light travel in a current universe? And that's define the event horizon where we can see things. You know, say there's a maximum limit that the light can reach us. That's called event horizon. So if something outside the event horizon is moving faster than the speed of the light, so we never know it's there. We cannot see it. We cannot receive any information from there, so we don't know that. So that's why it's called event horizon. So then universe lose contact outside of the event horizon. We never know, we don't know the way to know what's happening outside the event horizon. So we think about a little bit about this. Okay, then should I go through this? Okay. Okay. So let's do a little bit. So the light travels the shortest distance. When there's two places, light travels the shortest distance. Okay. Then so you can show the Friedman Robertson metric for the light becomes like this. It's going to be CT, shortest way. Okay. Then in a two different time frame, T and T1, if you take the ratio, of course the ratio is difference in time times this. This, if you remember, this is the here, the scale factor of the universe in case of lambda equals 1. Now I'm thinking about omega lambda equals 1. Okay? Then the distance is this, right? This is 1. This is co-moving distance, right? R1R is co-moving distance, right? And distance, then you integrate for the light travel distance from some time to infinite. And then you integrate this. And then if you calculate, you get this something like this, C over H, if you put Friedman equation here. So this is the maximum distance the light can travel between time T1 to the forever in the future. So this is the distance of the event horizon. This at some time T1 to the forever in the future, light can only travel this maximum distance light can travel. So this is the cosmological event horizon, and then you never see anything beyond this distance. And then please pay attention, this is decided, Hubble parameter decides about the cosmological event horizon scale. Okay? Question?
Is the event horizon distance change with time? Because since we know that
Yes.
we calculate the Hubble constant, it's not actually a constant.
Yes.
It depends on the redshifter.
Yes, right. That's right. Yes. It depends.
So what is the current event horizon distance here? Maybe say light years. How large is the distance?
So we can put the numbers here. C divided by
Okay,
L.
I will do.
That's okay. Well, we think about this. Okay. Okay. So, what's interesting? So, this is very interesting. It's like a black hole, but black hole also has an event horizon, right? So, in a black hole, there's a strong gravity, And then if have you heard of that? That even if the gravity is strong enough that even light cannot come out from a black hole, and then that boundary is called the event horizon for black hole. It's the same thing, but it's the opposite. In case of black hole, the event horizon is around the black hole, right? In case of the universe, event horizon is around us. And then it's interesting that so for example, in an Anson is here, right? And then our universe is expanding. So I can still see Anson, but our expansion speed gets faster, faster, faster. And then at some point, Anson's our expansion speed becomes faster than the speed of the light. Then I cannot see Anson anymore, right? When Anson's moving faster than. But you never see Anson disappear from your view. So I see Anson, right? And I see it. Oh, Anson disappeared. I cannot see it. This never happens because there's a time dilution. So when Anson comes close to the event horizon, the time is going to slow down. And then so actually from my viewpoint, he never crosses the event horizon. He floats it at the event horizon. It's the same thing as black hole, right? When something goes into a black hole, say Ashwin fall into a black hole and then die, I never see you die because on my side. Because when you go close to the event horizon of the black hole, your time frame is going to be very long for me, and then it becomes forever near the black hole event horizon. So for me, the maximum I see is you stop near the event horizon. So the same thing happens to Anson too. Okay. Then, do I still have time? Maybe I have. Okay. So then, let's look at the. Okay, so then let's look at our future of the universe. So now we know cosmological parameters, we know the universe is going to keep expanding with accelerated expansion speed. So what happens? Also, we talk about event horizon. See here. What happened to the future? Okay, let's look at the future of our universe. So I think this is interesting. So this is going to, for our current understanding, this is what happened to your future. Okay, I'm going to tell you what happens to your future. You're going to be a, I don't know, millionaire, or you're going to be homeless. That's what I'm going to tell you now. Okay, according to the Friedman equation. Okay, now let's start from easy one. From 4 to 8 billion years from now, Andromeda galaxy and our Milky Way galaxy merges into one. This we know that because Andromeda galaxy is closing to us with a 770 kilometer per second. It's a very high speed and it's closing. So in 4 giga years, it's going to be a collision. And this is actually very spectacular here. See? So this is Andromeda. This is some artist image. It's not real image. But then this is Milky Way, right? And the Andromeda galaxy is going to come very close to us, and eventually it's going to collide. Maybe could you turn off the light for just 2 minutes or so? Is it better?
Yes.
Then here. So currently Andromeda galaxy is something like this, right? Small. But it comes closer and then start colliding. And then when it collides, because there's a perturbation, there are a lot of star formations going to happen. So these red points are where star formation is happening. Here, a lot of star formation is happening. So this must be spectacular. Even if even now, if you go to some mountain or very dark places, the Milky Way of our galaxy is beautiful, right? We have two, and there will be very violent star formation, so it will be spectacular. So please live long enough to take pictures of this.
Possible.
And then star formation, and then two galaxies start to merge, and eventually these two galaxies merge into one giant elliptical galaxy. And that's also spectacular because we are inside this Milky Way, one elliptical galaxy, so the view will be very spectacular. So that's going to happen in 4 to 8 billion years from now. This is very simple version of the simulation. So I don't know, it's the Milky Way, and then there's Andromeda coming. This is Andromeda. Andromeda is about twice bigger than Milky Way, and this M33 on another galaxy, and then okay, here's the time scale. There's 3 billion years. It's going to collide. And then merge into one elliptical galaxy. But this one's going to merge? Maybe. Okay, so I don't know, 5-6 billion years, we will be in an elliptical galaxy. Maybe this one is going to be a satellite of Earth. Okay, so that happens. That's fine. That's still peaceful way, peaceful period. And then okay, could you turn on the light? And then now, about 10 to the 11 years or 100 billion years from now, so our galaxies in like Milky Way or Andromeda or local group, we are bound by the gravity. So we're not affected. These local galaxies are not affected by the expansion of the universe. But other distant galaxies are going to be far away, right? I'm talking about 100 billion years from now. So other galaxy becomes too far away, and then we cannot see them anymore. So that happens 100 billion years now. We can only see nearby galaxies that's bounded by the gravity, but other distant galaxies, like the one Alex distributes, distant galaxy, we cannot see or observe anymore. This is kind of sad universe, isn't it? If you are born suddenly in that time, you never know there are many galaxies in the universe. You can only see nearby one. Okay, then okay, here. So the culturally impossible. So the event horizon is going to come to the beyond the local group. Everything is beyond the event horizon. And then now, 800 billion years from now, galaxies begin to faint. Okay, so yeah, like 800 billion years, the galaxy stars, start to die, and then galaxies becomes fainter and fainter, fainter. And then here, 2 trillion years, there will be no way to see other galaxies beyond the local group. Even the gamma ray they emit will have the longer than the size of the observable universe. So the other galaxies are so much redshifted. Even gamma ray becomes longer wavelengths than the size of the universe, so there's no way to observe other galaxies. And then 10 to the 14 degenerate air. After 10 to the 14 years, the star formation will end, and then all the so there's no more stars going to be created, and then all the stars going to be degenerate remnant. So that means neutron star or white dwarf or black holes. All the stars die. Okay, so there's no more stars, no more sun, or no more stars. Okay, I should have talked at the beginning, but sorry, our sun is gonna die in 4 billion years, right? It becomes a red giant, our sun. So it expands, it's burn all the hydrogen, then it starts burning helium, and then it becomes the size of the orbit of the Mars. So the Earth is actually swallowed into the sun. So that's when you're going to die. We all die at that time. Oh, too bad. Sorry. Okay. So maybe we cannot see the Andromeda collide with Milky Way because the sun is already expanded already. I should have said that. And then, so 100 trillion years, the star formation is not going to happen. So, is anyone doing research on star formation? No? No? Oh, okay. Then you're safe. Okay. Then after 10 to the 14 years, there will be no star formation. So universe is going. There's no more new star, so the universe becomes dark. There's no more star in the universe. So it's just dark. Okay. If there's the merging of white dwarfs happens, then there may be a little bit light. That's the only thing. And then in 10 to the 15 years, then orbit of the planets decay. Yeah.
What do you mean by decay?
So, due to the gravitational radiation, so even the planet's orbit is going to decay and then either fall into the central star, or it's encounter with another system and kicked out of the planet system. So we start losing planets 10 to the 15 years. And then 10 to the 20 years, stellar remnants also escape galaxies or fall into black hole. So now we don't have stars, we start losing planets, but then we have those black holes and then neutron stars, white dwarfs floating, right? And then even these objects are going to fall onto the central supermassive black hole, the Milky Way, or they are kicked out of galaxies. So they are flying into the Milky Way. They sometimes encounter each other, right? And then when three body encounters, they kick out one of them, right? And then gradually they are kicked out of Milky Way galaxies. Okay. Well, this is very rare encounter, but in a long time, it can happen. And then in 10 to the 34 years, nucleons start to decay. 10 to the 34 is the lifetime of this nucleus, right? The proton lifetime, half-lifetime is about 10 to 34 years. So 10 to 34 years, those nucleus start to decay. Oh my God, the universe is ending, isn't it? So, and then by 10 to the 40 years, all nucleons decay. So we cannot exist anymore. So there's no nucleus, no atoms in the universe. It's all decayed. Too bad. And then after 10 to the 40 years, it's only black hole. There's no atoms in the universe, no light. Only thing remains in the universe is black hole. Okay, so that's black hole era. And then, okay, black hole era is going to continue for some time, but even black hole is going to evaporate. Have you heard of Hawking radiation?
Yes.
I think maybe I might talk about in the semester, but Hawking, so black hole is going to lose energy because of the Hawking radiation little by little. So even black hole era, that's the only thing in the universe is black hole. Black hole is going to lose energy and evaporate. That happens after 10 to the 100 years or something like that. Oh. Yeah. Okay. So then after 10 to 100 years, the universe is almost empty. There are maybe few remaining photons, neutrino, electrons, positrons, but the universe volume is so large they don't interact, they don't encounter each other. They're just alone. So gravitational, there's still dark matter. So dark matter's gravity is there, but dark matter is not going to emit anything. And the universe is going to be very, low energy state. Okay. So that's the future of our universe. Are you happy?
No.
It's almost, we are going into empty universe. You like empty universe?
No.
Oh, okay.
Actually, it sounds a bit ridiculous to me because there is a problem because we know that the mass is neither the spherical radius, but at the end of the universe, all the matter is gone. All the matter is gone.
Yeah.
But matters cannot be destroyed globally speaking.
Yeah, but it can become low density, right? Matters can become energy, right? Matters can become energy. So all the matters becomes few photons, neutrinos, or positrons. Anyway, so this is a summary of what I said. Okay. So that's the future of the universe. Very, very dark future of the universe. Congratulations. Okay, maybe I stop my lecture here today. Next week, I don't know what I'm going to talk about next week. Oh, next week we're going to talk about cosmic microwave background.
No, next week.
Another interesting. Okay, 2 weeks from now. Okay. So please look forward to that.